Okay, here we are. Free response practice 2, question 2. I'm going to get my timer going. Remember, I'm going to try and approach it as if I was taking it for the first time. Since this is question 2, the paragraph response, you should be doing this in approximately 15 minutes. So we'll keep an eye on the clock. Get ready. Here we go. And, I got to restart my clock. Reset. Start. All right, let's see. It says right here, block P of mass M is on a horizontal frictionless surface and is attached to a spring with spring constant K. Okay, yikes. I got a block attached to a spring. Looks like it's moving. Seen this kind of thing before. The block is oscillating with a period of TP. Remember, T is that symbol for period. Okay, the period of the block P as TP, okay, an amplitude AP. So when this block is here, it gets to a certain amplitude, say AP. That's a certain distance from that equilibrium spot. All right, a second block, Q of mass 2m, is then dropped from rest and lands on block P at the instant it passes through the equilibrium position. Let me read that again. 2m is then dropped from rest and lands on block P at the instant it passes through the equilibrium position, as shown above. Block Q immediately sticks to the top of block P, and the two-block system oscillates with period TPQ, oh my gosh, new period, and amplitude APQ. Okay. So this block here seems like it's oscillating back and forth, back and forth. There's no friction. Back and forth, and then this other block is dropped on top. It seems like it's still oscillating, but they're giving us new labels for the new oscillation period when there's that extra block on top, and a new representation for the amplitude, how far it's being able to move. Okay, let's give it a shot. A, determine the numerical value of the ratio TPQ divided by TP. Determine the numerical value. So it seems like they want a number of TPQ divided by TP. Okay. Now, I'm going to butt in a little bit. Obviously, we're not writing equations for this year's test. Okay. This question might not be a great mirror for what you're expected to do, but it's still valuable. Because one, you still might have to analyze equations, but also, how do you figure out the period of a spring oscillating back and forth? Do you know how to do that? Because if you approach it from like an energy standpoint, or using momentum, or using constant acceleration, none of those things are valid. Hopefully this question reminded you that the period of a mass oscillating on a spring is equal to 2 pi times the square root of m divided by k, where m is the mass of the block and k is the spring constant. Okay, but let's just go through this this math. All right, now for TP, that's going to be 2 pi times the square root. It's just when I had this mass here, so that's just m. Oh, this is going to look just like what I have up here. And k, let's remember, do they have any special letters for the spring constant? Frictionless surface is attached to a spring with spring constant K. Oh, they're just calling it K. Okay, so I can just keep calling it K, like this. All right, so that's when it's just block P. Now, when it's block T, P, and Q, that's going to still equal 2 pi, still the square root, m. Now, what's the mass? It's 2m plus m. They're combined, right? Well, that's not 2m squared, that's 3m. And divided by, it's still attached to the same spring. Okay, they make a point that this block is sticking. This would be a tough problem if this thing could like slide back and forth on that bottom block, but it's just sticking. Okay, now it says to find the ratio, and let's make sure I get this ratio in the right order. TPQ divided by TP, that's what they're asking for. TPQ, that's this one, 2 pi times the square root of 3m over k, divided by TP, this one, 2 pi divided by the square root of m divided by k. All right, well, what do I see? The 2 pi cancels out pretty easily. And then I have this square root. Now I have the square root of 3m over k divided by the square root of m over k. That ends up just being the square root of 3. Or if you plug that into your calculator, let's see, I'm going to punch it into my calculator, square root of 3. I get right here. I get 1.73. All but in, they did actually accept root 3 on these solutions. It asks for a numerical answer, so to be honest, they might accept this, but I like to give them an actual numerical, I guess this is a numerical answer too, but I like giving a decimal answer, as you know. Now, if you weren't sure why I was able to reduce this, let me just very quickly, I'm going to keep the clock running. Okay, this right here, what I have right here, I could rewrite that as like root 3 times root m divided by root k all over right here, root m divided by root k. I'm allowed to do that. That's how square roots work. I mean, this is just as valid. And that's why I can see, I have root m and a root m, so that cancels. I have root k in a denominator divided by a root k in a denominator, so that cancels out. So this hopefully is obvious. Hopefully, yeah, you got those algebra skills, okay? But it does work out that you're just left with the single thing. The only difference, that's a 3, but it's underneath the square root sign, okay? Maybe if I have extra time, I'll go back and double check my algebra. All right, but let's move on. Okay, letter B. It says the figure is reproduced above. How does the amplitude of oscillation APQ of the 2-block system compare with the original amplitude AP of block P? Okay, so it's saying obviously when I had one block, it was moving back and forth at some amplitude AP, back and forth and back and forth and back and forth and back and forth. Now when I'm adding this 2 mass, this extra 2 mass, is that amplitude the same, back and forth, the same amount? Is it now going to travel a smaller amount? That's what this one's saying right here, a smaller amount like this. The same amount, this is the same amount, or a bigger amount? Is it going to be oscillating at a bigger amplitude? Oh man, okay, let's see. I'm not going to mark things yet. Let me just think about it. This block is moving. I'm adding the block right here when the spring is no longer compressed or stretched. Is the block M moving right here, though? Yeah, it's moving. So if I drop something that's a mass of 2m, and it just falls straight down, and it falls on something that's moving, well, I must be accelerating this top block, right? Because it just falls straight down, and then it sticks, but right as it sticks, it's being moved to the left. So it seems like there must be a force on this top block. There's a force that is applied to this top block that makes it accelerate to the left. There kind of has to be. If there was no force, it would just stay there. So block M applies a leftward force. Okay, so let's see. I don't have a lot of space, so I'm going to start writing above. So block M applies leftward force on 2M. Okay, well, that means by the third law, if there's a force to the left on 2M, there's a force to the right on block M. The bottom block applies a force on the top block, and by Newton's third law, the top block applies a force in the opposite direction on the bottom block. By third law, rightward force on M. So when I drop that block on it, there's going to be a rightward force applied to M. Oh man, it's actually due to friction. I'll butt in a little bit, right? That bottom block applies a frictional force on this top block, making it accelerate to the left. It's a static friction, but I'm not necessarily going to write that in. So there's a rightward force now on block M. That makes it seem like work is being done, because that's not any conservative force that I know of. So work is done on block M, and that work is negative because M is moving to the left, but the force was going to the right. Oh, okay. So if negative work done on M, its energy, oops, no apostrophe, its energy decreases. Okay. So there's a rightward force on M that's doing work on M. That's going to decrease the energy. So now block M has less energy. What type of energy does it have right here? It's at equilibrium, so it's no spring energy. It's no spring energy. It must be kinetic energy. Okay, so at equilibrium, that Ke has gone down. So it's total energy, because that's all the energy it has, its total energy has decreased. So the total energy of this block has gotten less. Oh, okay. So if it has less energy when it has all kinetic energy, that must mean that it has less spring energy when it's fully compressed. Because remember, when it's fully compressed, it's not moving anymore. So its spring energy has gone down. Okay, I'm going to move to another slide. So, block A's, oh, was that what it was? Block A? I'm sorry, block P. So block P's spring energy must decrease at maximum amplitude. Because there it only has spring energy, and we just said total energy of that block decreased, and its total energy has decreased. Okay, well, at maximum amplitude, E total equals 1/2 kx squared, because that's the spring energy. So if energy went down, oops, that should be a comma, x must have gone down. That's the only way, right? It's the same spring constant. So if by having that negative work on block P, if its energy has decreased, well, that must mean that when it's totally compressed or totally stretched, all the energy is spring energy at that point, and the energy has become less than before, x must be less than before. So the amplitude has gone down. Oh, the amplitude has gone down, which means the right answer should be, let's see, APQ, when they're together, must be less than when they weren't together. Yeah, let me think about that. Okay, I'm dropping 2m. That has to apply a force to the right on block P. So block P, there was negative work done on it because it's moving to the left, but there was a force to the right. So for block P, in my whole explanation, my system is really block P. So block P's energy went down. So even though it's attached to this other thing, just this system, block P's energy went down. Therefore, when it's at its maximum compression or extension, the total energy still must be down. It must be lower than it was before. So when it only has spring energy, that x must be less than before. Yeah, okay, that seems reasonable. Let me check my time. Oh my gosh, look at this. Tough problem. I'm at 14 minutes and 45 seconds. Okay, 14 minutes 45, so I don't have a whole lot of extra time. Let me say this about this problem in particular. Okay, this was how I first thought about this problem. When you look at the solutions for this problem that College Board published, they didn't start off with this work analysis, this idea, and it's a little tough. Maybe Mr. Thrasher has a weird brain, but they didn't start off with this idea that applying this block applies a rightward force on M. That's not super obvious. You got to think about it, okay? Though it is true. They looked at it with a conservation of momentum problem in mind. And it's funny because yesterday during virtual office hours, a student made a comment saying, mentioning conservation of momentum. And I said to them, oh, you have to be really careful using momentum for this problem because there's a spring, right? And that spring applies forces. And I think I recommended to that student, this was before I tried the problem. I said, oh, I don't know if I would use momentum. So my brain, when I see this spring, I didn't think to use momentum first. But you could have used momentum, and it would still be valid, because right when this block is placed on top, notice, it's at equilibrium. Is this spring applying an outside force right when it's at equilibrium? No. So for this problem, and this was their primary solution on College Board, okay, they said, oh, well, if momentum's conserved, remember, P naught equals P. What have I done? I have mv equals mv. M naught v naught equals m prime v prime. I've added mass. So if I've added mass with this 2m, I've lowered the velocity, right? Because I have to keep these two sides of the equation equal. So College Board's response, and maybe you guys did something similar, if you argued, oh, dropping this 2m would make the velocity less, well, that means the kinetic energy is less, therefore the total energy is less, therefore the spring energy must be less, and then you eventually start doing the same kind of derivation that I had. But in the beginning, I didn't use momentum conservation. I used the idea of forces and work. Both are valid. Both are physically valid approaches. Okay, and in fact, it turns out College Board would have accepted either one. Okay, but sorry, if you were at my virtual office hours, maybe I should have tried the problem and looked at the solutions before I held those office hours. Okay, but you should nevertheless be careful with momentum conservation. Okay, you can only use conservation of momentum when there's no outside forces. And every other time, except right when it's in the middle, there is an outside force acting on these two blocks. And it's tough to do momentum conservation with the spring. You really wouldn't do that. Like, momentum is not conserved for this system as it's oscillating back and forth. Anyway, those were my solutions. I obviously went over my time, but I wanted to talk about that extra explanation, okay? Tough problem. Thanks a lot for watching.